Okay, so this is the burette, okay, and we'll have a chemical that we're going to use to titrate the other chemical. So this chemical we're using is sodium hydroxide, and the molarity of this we know is 0.1 over. Okay. So what I do is I pour this into the burette. And I'm going to give you some numbers to write down here to help us do a calculation on this here. So right now, when I build this up, what I want to make sure is I don't go past the 0 mark on this. There's all these calibrations on here. It's not really important to get to 0. I just have to record the starting number and then the finishing number, and I just subtract them and find out how much chemical I actually have here. So right now, when I'm reading this, there's 0.4 0.4 milliliters as our starting point. And what I did before I set this up, so before you came in, was I did a trial run, and I just kept adding chemical to the solution. And see how dark pink that is? That's way too dark. Like I've added way too much of this base to this. And so what was in here, first of all, was acid. So the acid I'm going to try to neutralize is hydrochloric acid. And so that's HCl. And what I'm going to do is measure 10 mils of this. So that's the acid there. So I add 10 mils of this here. Add just a little bit. So right now, that's 10 milliliters. So we have 10 mils of acid. And what I'm going to do is pour this into a flask here. Right? So right now I don't know the concentration of this chemical, but I know it's hydrochloric acid. And right now the pH here should be well below 7. It's an acid, right? And what I'm going to do now is add phenolphthalein, which is our indicator, and its pH range is from about 8 to 10 roughly. Okay. So if I add this here, it's going to be color. It should be below 8, which is colorless. So there's just no color to it. Okay. So a few drops. Swirl it around, just mix it in. And so once again, I can't tell anything. It looks exactly the same as it did before. But when I add base to it, if I add enough base, it eventually will turn pink. So if I add enough base to it. So basically, I did this before you came. So I have the acid here. That was acid, but then I added a certain amount of base to it. And generally with a titration, what you do is you kind of add like 2 mils at a time, or maybe 4 mils at a time. And the first time you do it, you basically overshoot the mark, right? So when I did this here, I added 22 mils of base to this, which obviously is too much base to do that. So what I want to do is have like a light shade of pink here. So what I'm going to do is add base to this. I'll just do one try. We'll ballpark the numbers here, okay? But normally you would probably do this 3 or 4 times till you get to a pretty accurate amount of base being added, just because we're times tight here. So I'm going to add kind of 5 mils at a time. You can kind of see as I do that, it's going to turn pink, and it kind of goes pink again, right? So sort of watch that. So you see that pink forming there. So that's almost 10 mils of base. That's quite a bit of base. And then it just give a swirl, and it completely goes back to being clear again, right? And so that equivalence point is reached pretty quickly here. So I did 22 mils. So I'm going to add 5 more. So that should be okay. It's gone again, right? So now I'm about 15 milliliters in. And I'm going to start adding smaller amounts now so I don't overshoot the mark. So once again, that's just too dark. I added way too much base there. So I'm going to add maybe a mil at a time. a bit longer to get rid of the color change. So even that's almost too dark. So I was basically a bit generous there. But you can see it's pretty light, like it's quite a light pink. And so this final measurement here, that is 19.1 milliliters. So let's record that down, 19.1 milliliters. And so what we're going to do is we're going to figure out what is the molarity. Just doing one trial, it's kind of gone now, right? So I'm probably close to there. What we're going to do one trial, and then we're going to see how we do the calculation on it, basically. Okay. So I'm just going to turn this to face forward. And okay, so we're going to use sodium hydroxide. And that sodium hydroxide is 0.10 molar. And that was our standard. So that's the thing, we knew the concentration of. And we started with 0.4, it's actually 0.40 milliliters in the burette. And then we added it, we got to 19.1. So basically, we started with that amount, and that's how much we got. That's what we read after we did that. So we want to subtract these two numbers. And so we do that. So we go 19.1 minus 0.4. That gives me 18.7. 0. Okay. Now that's the amount of base we had to neutralize the acid. So what we want to find out first of all is moles of base. And you can't work in millimoles if you want, but I'm going to work in moles. This video talks about millimoles here. So all you do is take your molarity, 0.10 moles per liter. And you're going to times that by the volume. Is it one of our students? So it times that by the volume, but I'm going to convert that to liters now. So 0.01870 liters. And so basically I just move the decimal one over. So 0.00187 moles. So here for that. So that's the moles of base we use. And of course, the moles of OH minus will equal the moles of the NaOH. Because for every one NaOH, there's one OH group that we can use. And then because we knew we reached equivalence point, we can say the moles of H plus will equal the moles of OH minus. So that's the definition of equivalence. And we do that because the phenolphthalein turned that color to allow us to number red that zone. So basically, the moles of H plus, the moles of OH, and the moles of NaOH are really the same number here. Now, where this can change, though, is when you try to find the moles of the acid. But the acid itself is a monoprotic acid that only has one H to give. But something like H2SO4, that would be diprotic, so this number would change now. But since the moles of HCl are going to be equal to the moles of H plus, and we know that they would also equal 0.001870 moles of the acid itself. And then the final step is to figure out the concentration of the acid, concentration of the HCl. And that would be equal to the number of moles divided by the volume of the acid. So that's 0.00187 moles of acid. And then the volume of the acid that I measured was 10.0 milliliters. It's 10.0 mils. So down here I write 0.0100 liters. So divide that by 0.01, sorry, 0.00187 divided by 0.01. That gives me a concentration of about 0.187 and a sig figs, I guess, 0.119. Is that okay for that? So that's sort of the calculation step here. So we are wanting to show this kind of understanding that you know the OH equals the NaOH, the H plus equals the OH, and so on. So the only thing that would change here is if it was dichroic, like let's say, just for example, let's say it's H2SO4. And at this point here, the moles of H2SO4, if that was the acid to use, you would have to say there's this many moles of H plus, and then you want to divide it by 2. Because for one H2SO4, you actually have 2 H pluses. So you would have the concentration, half the number of moles, would have been there. Because the H2SO4 would have been quite double the number of protons to neutralize things. But that was just for questions. Is that okay for sort of how indicators kind of work? Sorry, how titrations kind of work? Okay. The other thing I was going to talk about was about indicators and buffers at the same time. I'm just going to kind of move that there. Just move my apparatus out of the way. Okay, and one of the chemicals that's used for indicators is brothinyl blue. I'm not sure if that's on our data sheet. Brothinyl blue. So brothinyl blue has a pH color change from 6 to 7.6. 6 to 7.6. So it's fairly close to neutral conditions in that case. And so what I'm going to do is add that to just empty beaker. Just a few drops. So brothinyl blue. It's kind of a greeny color right now. And then what I'm going to do is add just a little bit of water to that. Some water here. And so we know water should be around pH 7 roughly. Depends on the temperature of the water, but close to pH 7. So I might need to add a bit more chemical. It's hard to see that. And indicators, what they are, they're actually organic weak acids and bases. They're able to manipulate their color depending on how many protons are attached to them. So they're kind of a bluey kind of color. And it says that brothinyl blue should be blue if it's above 7.6 and yellow if it's below 6, right? So this actually is maybe kind of a combination of those colors, being water. Maybe I should be somewhere in the middle zone there. And so what I'm going to do is take some hydrochloric acid and add that to a small beaker here. Okay? So it should turn more, which way do you think? More, yeah, more acidic, right? And so do you think become more yellow or more blue? More yellow, yeah. So hopefully, I haven't tested this one yet. That's what she does. Fairly yellow there. And then, yeah, quite yellow now, right? So it just takes a bit of time. And then the base, I'm just going to, this is the sodium hydroxide we use in the titration. Just pour a little bit in there. And quite blue now, right? And then you can kind of mix them, like you can kind of like pour them together. It kind of neutralizes it, right? So it's neutralizing it. And still neutralizing it, right? So it just takes a bit of time to neutralize it. We can maybe pour that in here, but it's still blue. Well, maybe light blue. And that would have meant there probably was more hydroxide present in total. Really. So another chemical we can work with is, where is it here? Universal indicator. So this chemical here stains your clothes. Working with this stuff, but also stains desk surfaces and your fingers. But it actually has like about 10 different indicators in here. It gives you a spectrum of colors you can actually witness. And so in just one chemical. So if I grab a beaker and I pour just water into it. And I add some universal indicator. It's kind of red when it goes in, but for water, it turns into kind of a greeny color. And so that's sort of around pH 7. And then if I have, say, some acid. So if I add universal indicator to an acid, it goes a red kind of color, it turns red. And then if I take a base, take a base and add it to a base, it goes purple kind of color. And that's actually a strong base, that's a strong acid. And so if you were to use a weak acid, you actually get a yellow color. And if you use a weak base, you get kind of a blue kind of color. And it has this whole spectrum of colors that you can work with here. And that's just because the indicators go through, I remember that word endpoint. So the endpoint of an indicator, it's a really bad name, it's the middle of its color change. So it's when you have equal amounts of both chemicals. So they use the word endpoint, but they also use the word transition point, which I think is a better word actually. So transitioning between one color and the other. But the endpoint is the place where the indicator is in the middle of its color change. And then from our graph we saw right in the board there, that's the equivalence point of a titration. So I kind of go through those again because that's like they sound very similar. So endpoint and transition point are the same thing, and they're for indicators, and they're basically showing us how the pH. Sorry, they're showing us the change in color of the indicator. Whereas the equivalence point is what we do in a titration when we know we neutralized the chemical. Still recording, okay. Okay, and I was going to talk about, just since we're here, let me see if I can tear off one of these ends here. There we go. Okay, so I just took a pipette and I'm going to use something I usually rather use a straw for, so I can splatter chemical. But so remember we said that this green color is pH 7 roughly, right? And if you're in like the yellowy, orange, red spectrum, it's more acid. And so at the end of the chapter, we study oxides. So we look at metal oxides and look at non-metal oxides. So things like nitrogen oxides, sulfur oxides, they tend to produce acid rain. But I can actually produce acid in here because I exhale CO2. And so if I just take this little straw that I made for myself, and I'm not going to drink it, because that would probably be very sick, but I blow into it. And we can see the color now is a yellowy color. And that's different than the original green color, right? And so basically the CO2 that I breathe into that has mixed with the water to produce carbonic acid. And so if you look on your data table under the bronchodilatery acids, if you look under carbonic acid, which is also CO2 plus water, it's kind of just below halfway down the table. If you look like right over here, I think it shows you CO2 and water. So that's actually carbonic acid, which is what I just made there. So you can just make that. And so in your body right now, when your cells are producing, when they're doing cellular respiration, they produce CO2 as a byproduct. That's one of the byproducts. And so that would cause, just if you didn't deal with that, that would cause the pH in your body to drop to like 6 or 5 or something like that. It's just manufacturing of CO2. So to get around that, our body has these things called buffers in them, which allows pH to stay relatively constant. And there, the last thing I was going to demonstrate here was a buffer. So we've shown titrations. We've shown kind of how indicators kind of work, kind of the general gist of that. And there's lots of videos on the math of how that works. The last thing I was going to look at was a buffer system. It's coming here, and sorry guys, watching there, you can't see the color. So, so this is still the acid. What's interesting about this though is this is dissolved CO2, and it's in an aqueous form right now. But if I let this sit overnight, the CO2 that's in here will leave the system, it'll go back to the atmosphere, and this will turn back to green again actually. So it's kind of an equilibrium between the CO2 in the atmosphere and the CO2 that I put in here. And it will actually allow some of the CO2 to leave. So acid rain generally is more acidic than that though. So places like where we have acid rain, you're looking at pHs like below 5.6 or something. So normal rainwater coming down is actually partially acidic just because it passes through the atmosphere. So let's take a look at our buffer here. So the buffer system, over here, where's my buffer? This is a buffer. So this chemical is buffered at pH 7. So it tries to resist pH changes at 7. So what I'm going to use is a control. So I'll just use water, just regular tap water. And I'll use another for my buffer solution. And I'm going to use your universal indicator again. So these should be close to the same pH. They're going to be off a little bit, but they should both be pretty close to 7. Unless there's something in the beaker. Yeah, but they're both kind of a greeny, slight different, but a greeny kind of color, right? Now, this acid is the one we use in the titration, and that's around molarity 0.2 reference, about 0.2 molar solution. And so that's actually really concentrated. Like I would not want to drink this, right? So if I negative log that number, that's almost around 1 or 2, or around 1, I think, right? So it's about pH 1 roughly. So I'm thinking that's quite dangerous. It's way more dangerous than my stomach acid is. But it should cause a drastic change in pH if I add this to a beaker. So if I plop this in to the water solution as your universal indicator, I'm just going to add a single drop. There's just one drop in there. Let's give it time. It's going yellow. It's going orangey. And I think the orange is around pH 2 or 3 around there. Okay, so that's a single drop of acid went from pH 7 to pH, let's say 2. So that's 5 pH units difference, which is 10 to the 5 times more acidic now than in a single drop, right? Which is why I really should be wearing eye protection, because that single drop that was to enter my eye would do the same thing as it's doing to that beaker, probably more so because there's less fluid in my eye. And so this is why you should always wear safety glasses, which is what I'm doing right now. So anyway, I'm trying to be safe. Okay, so there we go. So that's one drop in that. Now if I take it to my buffer solution, so this is pH 7 roughly, same as the water, right? And I add a single drop. Give it time. And it doesn't matter how much time I give it, it's going to stay that color. So I'm going to add like 2, 3, 4, 5, 6, 7 drops. Still green. Still green. So it's a 6, 7, 8, 9, it's a whole bunch, I just pour a whole bunch in there, okay? And maybe, I can't even tell, but I think that's a little bit lighter green than it was before. So I can just really go to town on this thing. So the video can't really show that, but I'm adding huge amounts now. I'm adding probably 50 drops to this thing. And it's still not even the same color as my breath was able to do that, right? So this clearly is resisting pH changes, right? So what's in here is a weak acid and a weak base, conjugates of each other, and they're basically acting across from each other. So the weak base in here is neutralizing the acid that I'm adding. And so if I was to really get crazy here and start pouring this in, I can overload the buffer. What just happened there is I added so much acid that I used up all the weak base that was in there. It's been completely converted to acid now. So the buffers don't stop pH changing altogether, they slow it down, they reduce the effect of it. But I can easily fix that by adding a bit of base to it. And my base here, I think, was this one. And just to show you how dramatic this is. Remember, this was the one drop of acid in the water, turned it from green to orange or yellow kind of color. I'll just do the same thing with the base now. I'll just add a single drop. There's my drop. Now the acid is a bit more concentrated. Oh, maybe not in the bases. But that's well past green now, right? If I add another drop, I'm definitely getting a bluey kind of color forming in there. I'm not sure if I can go over that. Yeah, there's the purple sort of form now. So I'm getting purple forming in there. It's kind of hard to see from your sitting, but it's a bit more purple there. So this buffer now has been overshot. I've overshot the buffer here. And that's because I added so much acid to it. So I'm going to add base to it now to show that you can actually shift the buffer back to its sort of happy place. Not sure how much acid I added to this thing. It's definitely going more yellow. I added a lot of the acid and base are different concentrations here. So if I give that time, it's going to become more green. But notice it's not going purple as quickly. Like I'm adding huge amounts of chemical here. And so I'll just take my original sample. This is just the buffer. That was the buffer. No. Just do one more buffer in here. So there's my buffer with some universal indicator. So buffer with universal indicator green again. And once again, I can add, if I take, this is the stuff I breathe acid into, right? So if I take this and add one drop, because there's no buffer in here, you can see just adding a single drop to that changes the pH already from an acid well into the base range of things. But here's my buffer. If I add base, or sorry, add base to this, no change, no change. And I'm adding huge amounts of base to this. So once again, the buffer resists pH changes, but it is going up in pH, it's not very much. So in this thing here, this tube, we have a weak acid and a weak base. And so depending which chemical you add to it, that other chemical neutralizes it. So if I add a base to this, it's the acid in here that neutralizes that base. If I add a base to this, it's the acid in here that neutralizes that base. So once you run out of that chemical, though, you can't stop the pH from changing. That's why it went dramatically in those cases. So I'm just going to stop the video there. That's probably good enough for that.